Selinger, who, as told us yesterday, works on, well, would you call yourself an experimental or theoretical?
Theoretical, but theoretical, computational,
computational,
simulational. Great.
So we have a pointer.
A pointer, so I can
give you a laser pointer.
Either way. Great. So my goal is that by the end of today's session, everyone will know something about how to model topological defects. So let me go here. Okay, so I'm from the Liquid Crystal Institute at Kent State University. Jonathan is from the same institute. If anyone is interested in pursuing graduate work or postdoctoral work at the Liquid Crystal Institute, please talk to one of us. Or if you have a friend, a sister, a brother, a cousin, an acquaintance who wants to study at Kent State, please come talk to us. We're always recruiting. Okay, so let's just start with a general discussion of defects. Today we have mostly talked about defects in soft condensed matter. I want to remind you that in crystal and solids there are also defects. So in particular, there's a kind of defect in a crystal called a dislocation. There's other types of defects. Grain boundaries, vacancies, interstitials, impurities, cracks, and on a free surface you can even have molecular or atomic height steps. Those are all different types of defects. And they control material properties, mechanical response to stress, ductility, brittle behavior. All those things are determined by properties and dynamics and pattern formation of defects. Okay, general properties. So I have a little video here. So this is supposed to be a simple two-dimensional crystal. It has a square lattice. And if you shear it, the top with respect to the bottom, you can nucleate a defect called an edge dislocation, which is transiting through the system and results in one atom shear. You get a step on this surface. There would be a step at some far surface where the defect goes out. You want to see that again? This is what happens when you bend a piece of metal. Now, in this particular case, the defect is nucleating from the free surface. Defects can also nucleate in different ways in the interior of the material. But metals deform through the process of nucleating and moving dislocations. Okay? Now, when you have a dislocation, let me see if I can freeze the movie in the middle where the dislocation is in the middle of the box. How about right there? Oh, there's a picture anyway. You can look at that. There's a thing called a Burger's circuit and a Burger's vector. Have you heard of those concepts before? Some people are nodding. If you've never heard of a Burger's vector or a Burger's circuit before, raise your hand. Anybody? Okay, that's enough. Okay, so imagine that you took a trip to a new city and you arrived in the darkness of night and you went to sleep in your hotel and you woke up in the morning and said, let's go see our new town that we're visiting. Okay, so you get out of your hotel and you walk 1, 2, 3, 4 blocks east, 1, 2, 3, 4 blocks north, 1, 2, 3, 4 blocks west, 1, 2, 3, 4 blocks south. You're like, wait, where's my hotel? That's not where I started. Okay, what happened in the middle of that circuit? One of the streets came to an end. Where is that? This point right here. See that street? That street came to an end. Here it's half an atomic layer. The international symbol for a dislocation looks like a letter T with a long, like that, or like that, I guess more often. That represents the end of a layer. An edge dislocation is the edge of an incomplete layer in a crystal. Okay, and as you can see, that defect can move. That's called glide. We were showing you that's a process called glide, where the defect is moving. The difference between where you think you're going to end and where you actually end is the Burger's vector. That identifies the nature of the defect inside. Now, the great story about the Burger's vector is that there were two brothers, both named Burgers, I believe in the Netherlands. One was a fluid dynamicist and one was a metallurgist. Which one do you think came up with the idea of a Burger's vector? You would think it was the metallurgist, right? Because this is about defects in crystals. But that's wrong. It was the fluid dynamicist. Why did the fluid dynamicist think to do a line integral around a circle? Do you remember something about Stokes' theorem and a line integral and the vorticity inside the vector, inside the loop? Right? It was actually the fluid dynamicist who figured out the Burger's vector. Okay, the Burger's vector represents a kind of topological charge. In the interior of the material, if you shear hard enough, you can nucleate a pair of edge dislocations. Like if you shear the material really hard, one solid layer can break into two half layers which transit through the system, right? The sum of the Burger's vectors is 0 in that pair nucleation process, and it's a vector sum. Okay? There's another kind of defect called a screw dislocation. I have a picture here a little later. Has anybody here ever parked a car in a parking garage? Like a 10-story high parking garage. And you know there's those great spirals. If you go around the circle, you come back one layer above or one layer below where you started. That's a screw dislocation. And in that case, the Berger's vector is actually upstairs or downstairs. Okay. So for the edge dislocation, the Berger's vector is here in the xy plane, and the defect itself is, say, parallel to z going into the plane. So the Berger's vector and the sense of the defect, which represents the edge of this half layer, if you extended this into 3 dimensions, they're perpendicular for an edge dislocation. For a screw dislocation, the sense of the defect line and the Berger's vector are parallel. There is such a thing as a mixed dislocation where the Berger's vector has a component perpendicular and a component parallel. Okay, so the 2 mechanisms by which dislocations move in crystals are glide, right? So this defect, this half layer can essentially join on to, an adjacent half layer, and another half layer can be produced. So that is a process that occurs under stress. When you apply a stress, it actually pushes the defects around. That's called a Peach-Taylor interaction. You can calculate the force on the dislocation due to an applied stress. Okay, so this is all metallurgy, but believe me, it connects to what we're doing too. So that's a kind of, so the Berger's vector represents a kind of conserved topological charge associated with dislocations. In 3D, a dislocation is not a point, it's a line. Okay, and they cannot begin or end anywhere except a free surface, or they can close on themselves as a loop. So they're really interesting topological objects, right? You can have, from a free surface, you can have an arch, which represents a half loop, right? You can have all kinds of interesting structures. The one thing you cannot have is a dislocation that comes into the middle of the material and then stops. That doesn't exist. Okay, so it's a very interesting topological object. So kind of like spaghetti that never ends. No free ends. Okay, so dislocations can pair nucleate and they can pair annihilate. So for instance, if I have 2 screw dislocations, one with Berger's vector up and one with Berger's vector down, they can pair annihilate and disappear. They're attracted towards each other and they disappear in a burst of passion like Romeo and Juliet, self-destructing, right? I'm going to teach you how to do that simulation today. Okay. Now, we talked about point defects in systems with orientational order. Okay, nobody actually took their pen and put it around the defect. I'm not tall enough to reach up there, so I might need a really tall person, or else I'll have to move. You're taller than me. You want to try it?
Should I give you a laser pointer?
You can give me a laser pointer, but it's hard to do. Do you have a laser pointer that has like an arrow on the end? No. Just a point. Well, I can try it with the ones on the bottom. Here's what we mean by a Berger's circuit when we're dealing with a point defect. I can kind of reach this one. So this is supposed to be a +1 defect, right? So you take your pen and you put the fat end of the pen where the arrow is and you go around. That's what, whoa, excellent, okay. So you can see that going around. So that goes around by +2 pi. I'm going to call that a +1 defect. That's what we've been calling all day a +1 defect. Here's the -1 defect. Watch the pen. The pen is going counterclockwise around its axis as the whole thing is going around this way. So as I move the pen in the plus theta direction, it rotates in the minus theta direction. So that's a -1, and I'm not even still tall enough to reach that, so that's +1 half and minus half. But you saw all that stuff this morning, and you all understood it, right? So those are topological defects. So this would happen, for instance, in a smectic C. Nobody told you what a smectic liquid crystal was yet, did they? A smectic liquid crystal is I took that slide out of the top because I was sure you guys would have seen that by now. Okay, a pneumatic liquid crystal, has orientational order, right? Like rods in a box. Shake them up, Big 10 tool line. A smectic liquid crystal is a layered structure, okay? And in each layer, in the smectic A liquid crystal, the molecules are standing up. Actually, we happen to have a box of chalk right here, so we can use that. In the smectic A liquid crystal, in each layer, molecules are standing up, but their centers of mass are distributed randomly like a liquid. So, but they're very much layered in the z direction. So you have essentially stacked two-dimensional liquids. Okay, that's fun because you can have dislocations in it. You can have half a layer, you can have a screw dislocation in a smectic. A smectic C is one where the molecules are tilted with respect to the layer normal. Okay, that's a smectic C. Smectic A standing up, smectic C tilting. If I look from above at the tilt direction, I see a vector field. Because the tilt direction is an arrow with a head. The tilt direction is like an arrow. So in that case, a smectic C can have a defect like this or like that. So think of those as the tilt direction. So if everybody on this side of the room leans to the right, or my right, your left, everybody on the left side of the room leads that way, everybody in the front of the room leads forward, everybody in the back of the room leans back, we'll have a point defect in the middle, just like that. You want to try it?
Yeah.
Everybody lean. People in the front lean toward me, people in the back lean back, right? Now go the other way. Lean the opposite direction, right? The core of the defect is in the middle, and I can walk around and do my defect. Those are point defects, +1 and -1 in a smectic C, in a single layer of a smectic C. Okay. If we all lie on the floor, we can make defects like that. We can save that for after the beer tonight, okay? All right, so let's talk about statistical physics models that are the simplest way to study those things. We're going to learn a little later in the week, I think, about Frank energies, the Frank free energy for liquid crystal, and how we could do calculations. We're going to do something really, really simple. We're going to look at the X, Y model. So let's back up one step. How many people here know about the Ising model? I asked yesterday, but there's more people here. You've heard of the Ising model? Okay, I won't teach the Ising model. The Ising model is a simple model of magnetism that says if we have a spin, call it SI, that has two states, up or down, nearest neighbor interactions that says nearby spins want to point the same direction, it's lower energy, and if they point in opposite directions, it's higher energy. That's the fruit fly of the statistical physics world, right? Biologists study fruit flies because they're simpler than mammals, you know, and statistical physicists study the Ising model because it's simpler than any real system. The simplest possible thing, 1 degree of freedom, 2 possible states at each site. That system is really interesting. In 1 dimension, it doesn't have any phase transitions. In 2 dimensions, it has a phase transition, which was, you know, solved by Lars Ansager. And in 3 dimensions, it has a phase transition, which, as far as I know, has only been characterized by computer simulation, and nobody's actually solved it. So the Ising model is really great for studying statistical physics. If you've never coded it, I'd be happy to show you how. But today we're going to talk about the XY model. So the XY model, Hamiltonian, that H is supposed to be curly, it means Hamiltonian. Potential energy, right, is minus J, an energy coefficient, times SI dot Sj, where that represents a sum on nearest neighbor spins in some lattice. It can be 1-dimensional, 2-dimensional, 3-dimensional. Today I'm going to focus on the 2-dimensional system. So I want you to think about a square lattice of spins. Each spin now, instead of just having 2 states up and down like the Ising model, can point anywhere in the XY plane. Okay, so the spin only has 1 angular degree of freedom, has no translational degrees of freedom. The spins are not going anywhere. They're staying put and they rotate around their own axis. Nearest neighbor spins can be minimum in energy if they're parallel. SI dot Sj has its maximum when SI and Sj point in the same direction. J sets the energy scale, so it matters when we measure temperature, kBT, compared to J. J sets the energy scale. SI is a unit vector whose magnitude is always 1. It is not a scalar order parameter. It is not an index of a defect. So we keep using letter S for different things today. We should coordinate. There's only 20-something 26 letters in the alphabet, and we need a lot of them. Sometimes we have to switch and use Greek and Greek and Hebrew. Anyway, so square lattice. So if J is greater than 0, then the ground state has all the spins parallel. But the ground state isn't even stable, even at low temperatures. You get spin waves. And this XY model is really interesting. It has a phase transition called the Kosterlitz-Thouless phase transition, also known as second order melting. So in 2 dimensions. And so in 2D, the transition is at kBt. Actually, you have to divide by J. But it's a little less than 1, the phase transition. So below that temperature, it has some kind of quasi-long-range orientation order disrupted by spin waves. And at high temperature, it has only short-range orientation order. These +1 and -1 defects occur in this system and are seen in the high temperature phase. It's just disordered everywhere. You can think about that as like a vortex plasma. There's plus and minus defects everywhere. At low temperature, you can have a vortex, anti-vortex sort of form and annihilate and form and annihilate and form and annihilate. And then at the phase transition, the vortices kind of go free. Okay, so just to let you know, this is a +1 vortex, but this is also a +1 vortex. Okay, you can add a constant to any spin, and it doesn't change the energy. The energy only depends on the dot product between two vectors. If you add a constant to both vectors, the dot product stays the same because the dot product is cosine theta I minus theta j. If you add a constant to both of them, the difference is unchanged. So the only difference between one of these and one of these is adding a constant. So we would call that phase. So this is a -1 defect and this is a -1 defect. We have a name for them. We call them vortex and anti-vortex, which should remind you about matter and antimatter because they can annihilate, right? So a vortex is a +1 and anti-vortex is a -1. Okay, the first simulation method we're going to talk about is Monte Carlo simulation. This is a classical system. How many of you have studied Monte Carlo simulation? Just a few. Okay, have you heard the words detailed balance before? Nothing. Okay, we need to take a break from the slides for a minute. Okay, in statistical physics we learn that if you have a system that has a set of discrete energy levels, that the percentage of time that the system will visit each of those levels depends on the energy of the level. And what's the word, fugacity, the amount of time the system spends in each level goes like e to the minus energy over kBt. The Boltzmann factor, e to the minus energy over kBt. And we can build a partition function and we can calculate expectation values knowing what percentage of the time the system will be in each of those energy states. To break that down to practicalities, the system spends lots of time in low energy states, a little bit of time in medium energy states, and hardly any time at all in the high energy states, right? Depending on the temperature. If you raise the temperature to infinity, it will visit all the states with equal probability regardless of their energy. Okay, so that's why systems have phase transitions and so on. Temperature. If we want to do a computer simulation, if we have a system that has a countable number of states, so let's say I want to know everything in the world about a one-dimensional Ising model with 4 spins and periodic boundary conditions. You guys know about periodic boundary conditions? I learned about periodic boundary conditions from playing video games in the 1970s. Because if the Pac-Man went off one side of the screen, it came in on the other side. That's periodic boundaries, which means topologically, Pac-Man plays on a torus. Nobody ever tried to actually put a Pac-Man on a torus, but the periodic boundary conditions are equivalent to Pac-Man playing on a torus, which I thought was kind of interesting. Okay, so if I wanted to know everything about an Ising model with, say, 4 spins, I could write down all the possible states. How many states are there of 4 spins? 2 to the 4th power, 2, 4, 8, 16. There's 16 states of that system. I could write down the energy for each one. I could calculate the any expectation value of any property, say the magnetization, the sum of the 4 spins, summing over all the possible states, and get an answer, what's the magnetization as a function of temperature. There's nothing stochastic about it. It's exact enumeration. I can calculate the full partition function, know everything about that system. What if instead of 4 spins, I have 400 spins? Like, I don't know, a 20 by 20 square lattice. Or even a one-dimensional 400 spins in 1 dimension. How many states are there? What's 2 to the 400th power? It's a pretty big number, even for a computer. Making a list of all the possible states of that system is a very difficult problem computationally. And if you could even do it for 400, I challenge you to do it to 4,000 or 40,000 or 400,000 or 4 million. It's not feasible. Instead of doing an exact enumeration, a list of all the states, we're going to do a stochastic sample. Okay, this is what census bureaus and marketers do all the time. We can't ask everybody in the whole world the same question, but we can take a representative fraction of people and ask the question and get some idea about what's happening in the whole system. Likewise, we can make a stochastic sample of all possible states of the Ising model and get answers about expectation values. But instead of just generating states at random, we can actually do a careful like a Markov chain going from one state to another state to another state. And the idea of detailed balance, without spending too much time on it, is that if 2 states have 2 different energies, the ratio of time the system spends in the 2 states depends on the difference in energy, e to the minus delta energy over kBt. So if we can come up with a probability rule for going from one state to another state that has, or back again, with the right ratio, we'll get the right population statistics. And that is the origin of the idea of the metropolis algorithm, which is a technique for going from one state to another state and back again. And I will show you how it works. Okay, so here is the flow chart of a Monte Carlo simulation. We could talk about the Ising model, we could talk about the XY model. It's almost the same, not quite, but I'll explain. So we're going to start with, say, a 20 by 20 square lattice of spins. So that from the point of view of programming, you've just declared an array, let's call it theta, of ij, where I goes from 1 to 20, j goes from 1 to 20. That's my theta. Let me give every spin an initial value that's randomly chosen between 0 and 2 pi. That's my initial state. I have nearest neighbor interactions. The energy goes like si dot sj, which is cosine theta I minus theta j. Ooh, I just used I and j two different ways. Bad teacher. Okay, let me try to explain. I can be an index that's like x that runs from 1 to 20 on one axis. J can be another index that runs to 1 to 20 on the other axis. But when I write this Hamiltonian of Sij, where did it go? That thing? I just mean this little ij, I know that's tiny, I don't know if you can see it. That just means all nearest neighbor pairs. It means each spin interacts with the neighbor north, south, east, and west. It doesn't have anything to do with that other ij. It just means all nearest neighbor pairs. Okay, so here we are to our algorithm. So it's going to work like this. So we set up our random initial state of the system. I'm going to pick one of those 400 spins. I'm going to pick an I between 1 and 20. I'm going to pick a j between 1 and 20. I'm going to take that spin and I'm going to sum all its interactions with its north, south, east, west neighbors, and I'm going to call that energy E old. That's the energy of the state before I do anything to it, the spin. Then I'm going to take that spin and I'm going to make a little reorientation, say plus or minus up to 5 degrees, or maybe 10 degrees, something like that. Some little tweak of the spin. I'm going to calculate the new energy, E new. Okay. Now, if I just wanted to do energy relaxation, I could make a very simple rule. If E new is less than E old, accept the change, otherwise reject it. That would just move the system towards its nearest local minimum in energy. But if I want to study its behavior at a certain temperature, then I have to do this stochastic process called the Metropolis algorithm. It says if E new is less than E old, then you accept the move, the spin is reoriented. Otherwise, there's an energy increase of an amount delta E, which is E new minus E old, and that's a positive number, because I know already that E new is bigger than E old, right? And then I'm going to calculate a Boltzmann factor, which is exponential of that change minus that change in energy over kBt. I'm going to choose a new random number. If it's less than p, I'm going to accept the move. And if it's bigger than p, I'm going to reject the move and put the spin back to its previous position. That is the Metropolis algorithm in a nutshell. And this process of accepting the move with a probability that's 1 if you're going downhill in energy and exponential minus delta energy over kBt if you're going uphill in energy, gives you the detailed balance statistics that the amount of time you spend in one state versus the other state has the right ratio. Okay? Yeah?
I don't understand the random number part. If random...
Choosing a random number between 0 and 1.
Okay.
If p is a number also between 0 and 1, it's the probability of going uphill in energy. So if I choose a random number between 0 and 1, a fraction p of the time it will accept, and a fraction 1 minus p of the time it will reject. So it's just a way of flipping a coin with the probability p.
Okay.
Does that make sense?
Yeah.
Okay.
And this is just a normal distribution for a random number?
Just even flat distribution between 0 and 1. So the built-in random number generator in your programming language is good enough for this process. Doesn't need to be Gaussian, doesn't just flat between 0 and 1. But it must not be Gaussian or this won't work. Okay. Now there's a trick here. If we're doing this thing with the Ising model, what I'd be doing to the spin is flipping it between up and down and up and down. Only 2 states. But in the XY model, the spin has an infinite number of possible states between 0 and 2 pi. You can't count them. So I need to know something about the size of how much I'm going to reorient the spin, the small reorientation. Okay, and I'm going to adjust that so that the acceptance rate is somewhere around 40%, 40, 50, 60%, somewhere in that range. Okay, and that's just to speed the rate of convergence to equilibrium. So that's just another parameter to mess with to get that to be right. So let me show you a little movie. This is a 40 by 40 lattice. Can you guys even see those spins? I think so. So the initial state is random. There's periodic boundary conditions. Thank you. Okay, so I just quenched it to a temperature below the phase transition temperature. Do you see these defects? There's a +1 there, +1 there. Where's the -1? There's a, well, they're moving around so fast. There's a -1 there. You can't see the heads very well. You can't see the difference between the heads and the tails. I can see them better on the screen. Well, there's some defects there. Okay. The visualization with arrows is already hard to see at 40 by 40. Imagine if I were doing 200 by 200. All those little tiny arrows are hard to see. So instead of doing that, you guys already learned today that you can, if you imagine that this was a liquid crystal and that orientation was between cross polarizers, you would see a grayscale. And if you remember from Jonathan's lecture, the key intensity is sine squared 2 theta. Okay, so then the defects turn up as points with brushes, and I will show you what that looks like. Okay, and remember, Yvonne told you that when you rotate the polarizers around the sample, defects of opposite topological charge counter rotate. I'm going to show you that too. Okay, so here's a similar, again starting with the random distribution. This one's cooling gradually, I think. I ran these simulations last night. We can run them again in real time if necessary. So you can see this texture of defects is starting to form. And when it gets to the end, when it's nice and cold, then I have the system rotate the polarizers right, left, right. So let's see how that looks. Maybe it was left, right, left. Ooh, there was a pair annihilation. There it goes. Now it's rotating. Do you see how neighboring defects counter rotate? You want to see that again? Okay, so cooling, 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 going through the phase transition. The system's starting to form point defects, and you can see the brushes. So here's, for instance, you see the defect, and there's a brush, and there's a brush, and there's a brush, and a brush, and there's another one, and another one, and another. And they tend to form themselves into these chains. The brushes are all connected. Okay, and now here comes the rotation part. So where one rotates right, the other one rotates left. They alternate, positive, negative, positive, negative, positive, negative. Okay, this code is really short. I'm happy to give you guys these codes. In fact, I think if we have time, maybe I'll even show you one and we can go through them. You want to actually see this one now? The Monte Carlo, not right now? Some people are saying yes. Let's just take a break from physics and look at computer simulation for a minute. Okay, this is written in my native language, which is Fortran 77. And I did that on purpose because it's really easy to read. I didn't use any of my usual tricks to speed it up. I tried to make it as readable as possible. It still executes quickly on a PC. If you're a Fortran programmer, you'll be happy with this, but it's supposed to be essentially something that anyone can read and translate into any other language. It's very simple. So we have parameters here, and this is dimension at 200 by 200, but right now I have the system running at size 100 by 100, N2 is N squared. Pi temp is the temperature in units of KB, or in actual units of J. This is just open output files. This sets the theta initially to a random number between 0 and 2 pi. This is that parameter that says I'm going to be able to rotate the system plus or minus 5 degrees. And in old-fashioned Fortran, we label do loops with numbers, which makes it easier to keep track of which end statement goes with which starting statement, so I do that. Every 100 steps, I let myself know how much progress I've made. I need to calculate the acceptance rate. If I have a system of 100 by 100, I'm going to make 100 squared attempts, pick a site ij somewhere in the box. I plus 1 and I minus 1 are represented as IP1 and IM1, JP1, JM1. Periodic boundary conditions just says if those are on the boundary, go across to the other side. You calculate the energy of that spin you just chose, ij, cosine theta, I plus 1j minus theta ij. It's just the interaction with the four neighbors, si dot sj. The minus sign says the energy is lowest when the spins point the same direction. The lowest this energy could be is if each of those delta thetas was 0. Then this would be E old of minus 4. That's the lowest possible energy if all the spins point the same direction, right? The highest energy could be is plus 4, if they all point in opposite directions. Okay, I store the value of theta before I do anything to do it, just hold on to it, theta old. Then I add a tweak, a change to theta ij, add some small number that could be negative or positive to it, calculate the energy now. Then energy, the new energy is less than the old energy, then I just accept that change and I'm done. Otherwise, I calculate the change in the energy, delta E is E new minus E old. Calculate the Boltzmann probability. Choose that's P, choose a random number. If it's less than P, we accept. Otherwise, if we reject, we put theta back to its old value and we're done. Wasn't that painless? That's the shortest code. It produces the coolest simple thing, right? The only tricky part of this whole thing is that the size of the tweak, the amount of time of how much I'm going to reorient the spin on each time step, I want to adjust that. So look at the acceptance rate. Okay, if I have 100 by 100 thing, that means I have 10,000 spins, right? Out of 10,000 tries, what fraction of them produced an accepted move? If that number is too small, it means the moves I'm making are too adventurous, they're too big. I need to make my step size a little smaller. On the other hand, if my acceptance rate is too large, it means I'm not being adventurous enough. I have to take bigger risks. So I make it a slightly bigger. I also don't let that number get too big. I don't let it get above maybe 10 degrees. Okay, so that when it's cooling down, the thing doesn't get out of control. Every 25 Monte Carlo steps. One Monte Carlo step means I've made one, if I have a 100 by 100 system, and I'm choosing a random spin every time, when I've chosen 10,000 times, that's one per spin. Now, some spins might not have been visited, and some might have been visited more than once. Doesn't matter. It's on average. That's called a Monte Carlo step. Every 25 Monte Carlo steps, I output data. I'm using a free visualization software. Free is good because I don't believe the ICAM budget includes buying software for all of you, so I picked something free. I'm using one of my favorite ones called Sim Replay. It was written by a material scientist I know when he was a graduate student at University of Michigan. Sim Replay, it was designed for making videos of molecular simulations, but you can press it into service for darn near anything. So in this particular case, I'm using, I can either print vectors to see the individual arrows, or I can print dots that have a color on a grayscale between 0 and 1. If you decide you want to use this thing, let me know and I will give you a quick lesson in how to use Sim Replay because there's some parameters you have to set. But yeah, so the vector is cosine theta sine theta. That's basically what I'm plotting. Okay, so and then at the end, I wrote another little routine to make an offset of the angle going positive and going negative so we could actually rotate and see the defects counter rotating. So you know how there are many contests on television for who's the best singer, who's the best model, who's the best chef? I'd like to have one, who's the best programmer? So I teach a class in computational material science, and I have students doing essentially the same assignment. We can have an award for whose code has the fewest lines, because there's many ways to make it more compact. I mean, this is pretty low level in terms of abstraction. Or you can have an award for whose code runs the fastest, right? Or can handle the large, uses memory the most effectively. All different things to keep in mind. So let's see, we need to go back to PowerPoint. Okay, so look at the movie one more time and then we'll move on. So the defects are present both positive and negative. What do you think the total topological charge is in this box? This box has periodic boundary conditions. Has to be 0. Total topological charge is 0. Okay, so as many positive defects, we have negative defects. And if you actually count them when you do the counter rotation, you'll see, and they alternate plus minus plus minus. This one was just in the act of about to pair and annihilate. Yeah?
So when the movie ends, can you tell which defects are positive or negative?
Only from when they're rotating.
Yeah.
The still image does not tell you anything. Only the fact that when you rotate the polarizers, that they go in opposite directions. So remember, the plus defect goes with the polarizer and the minus defect goes opposite. Counter rotates. Okay, let's talk about defect. Oh yes, go ahead.
Is there a way you can set up the simulation so that there's no defects?
If you anneal it more slowly, because I annealed this pretty quickly. If you anneal it more slowly, the defects can pair and annihilate completely away. It's easier if the system is smaller. So the annealing process, the defects, well, we're about to talk about defect interactions. Positive and negative defects have an attractive interaction, but they have to overcome an energy barrier associated with the lattice. So I'll try to explain all those things. Okay, let's talk about defects of interaction. Dislocations in crystals also have defect interactions that are pretty easy to write down, and they're analogous. So two defects of the same sign have a repulsive interaction. Remember, log r goes to minus infinity at small r, so if you put a minus sign in front of it, minus log r goes to plus infinity. So that's the form of the interaction between defects of the same sign, okay? And it's the same form for defects of opposite sign. It goes like log r that goes to a minus infinity for r equals 0. Okay, but it doesn't really go to minus infinity. It's really log of r over some characteristic defect core size, which I should have put in the equation, but I didn't. So outside of the core size, the defect, and that core size would be comparable to the lattice spacing. So outside of that core size, the defect goes like the log. The force of interaction is the derivative of the energy with respect to r. So you get 1 over r forces that go like 1 over r repulsive for same sign and minus 1 over r for attractive for opposite sign defect. Yes?
So does that mean that there's things such as screening effects as one would expect from like a static?
Absolutely. Absolutely. And you can have essentially a dipole, right? Two defects make a dipole. Okay, so here's the question. If the temperature is below the KT transition, I mean, I quench those things down, right? Why don't all the defects paranihilate? Why do they get stuck in a metastable state if I anneal too rapidly? And the answer is something called the Pyros Barrier. So I keep going back to metallurgy. Pyros was old when I was young, so I can't imagine he's still with us anymore. But you can look him up in Wikipedia. He was a brilliant guy who figured out that when a dislocation moves through a crystal, it actually has to get over an energy barrier to get one local minimum, like between a set of atoms to the next local minimum, there's a little energy barrier. Okay, and likewise, when the vortex moves through the XY model because of that square lattice, the lowest energy place for the defect to be is in the middle of a square of spins, and then it has to go over an energy barrier to get between the next square of spins. So it has kind of a bumpy potential, and the height of that barrier is the Pyros barrier. So if you have a vortex and an anti-vortex, and they want, like Romeo and Juliet, they want to rush into each other's arms, right, and paranihilate, there's only one problem. There's this Pyros barrier. And so unless they're close enough that their attractive force can actually push them over the barrier, they can't move, they can be stuck. Okay, so heating this system gives you thermal fluctuations to help push over. So their attractive interactions can pull them over the barrier, or thermal fluctuations can help them get over the barrier. So the mobility of defects depends on temperature. Okay, and one of the reasons why annealing is so important in American society is that every one of us needs defect-free silicon for all the chips and all our electronic devices. And getting rid of all the defects is really important. So how do you anneal something? It means you put it in the oven and you heat it up maybe to half its melting temperature and then cool it very slowly. And the defects can diffuse, paranihilate, or get to free surfaces or whatever thing, okay? So I want to talk to you a little bit more about the analogy between a topological defect in the XY model and the equivalent metallurgical defect, which I said is the screw dislocation. So you see, this is our +1 defect. This is a picture of a screw dislocation. Okay, it's a little bit like the circular driving pathway in the parking garage, but it's made out of atoms. So if you imagine having a crystal, when you go in a circle, you go up one level or down one level. That's a screw dislocation. The screw is right here. That's the core of the screw, and it goes through the material. So you can make an analogy. When this spin goes from 0 to 2 pi, each one of these spins represents a column of atoms going up one lattice spacing, one Berger's vector, which is called by B. So if you set 2 pi in one case is equal to B, in the other case, there's an exact analog. So a plus defect could be an up screw, and a minus defect could be a down screw. Okay, so the interaction between defects is just like that. Screw dislocations in crystals have a Pyros barrier. Topological defects in the XY model also have a Pyros barrier. Okay, let's talk about, oh, did you have a question?
I was just wondering if there are any systems that don't exhibit Pyros barriers.
Well, see, liquid crystals are not living on a lattice. They're molecular systems. And so a topological defect there doesn't have a rigid lattice structure in which to navigate. And so we would not expect a Pyros barrier for the dynamics of these point defects, say in a freestanding spectic C film. They're living in a continuum, not in a discrete system. The Pyros barrier is a feature of the discrete model. Where I learned about this actually was not from the metallurgists and not from the soft matter people. I learned it from talking to the people who study magnetism. The micromagnetics modeling group at the National Institute of Standards and Technology in Gaithersburg, Maryland, the place that used to be called the Bureau of Standards. And in this, the micromagnetics modeling group was making different levels of approximation. They could discretize their system. I mean, just thinking about applied math, you can make a coarse mesh or a fine mesh and do the same calculation. And you always want to know, is my mesh fine enough to get a good answer? And what they discovered was that the topological defects in the magnetic systems seem to have this artifact that their mobility depended strongly on the size of the mesh. And they realized there's a Pyros barrier for dislocations, or for topological defects, that's purely an artifact of the mesh size. This is why it pays to sit with people at lunch who are not from your lab, right? You can learn from everybody. Who is wise? One who learns from everyone. So I went and talked to the micromagnetics modeling people. I even went to some of their conferences and learned from them. This is really interesting that you can mess up your system by taking too coarse a mesh, or you can introduce physical features that weren't present in the continuum system. Okay, now let's talk about the topological corral. A corral is a fenced place where you keep your cows or whatever animals you are raising, a corral. So how can I make a corral for a system? I'm going to make a wall. I'm going to make a wall and put my system inside. A defect corral. I'm going to fix the spins on the edge of my box. Do you see here? Let me see, I need my pen. Here's the pen. Pointing like this, and I'm rotating like this, and like this, and like this, and like this. The pen made a total of 2 pi rotation around the box. If I put an XY model inside this box, the total topological charge is determined by that integral. It's got to have a total topological charge of +1, right? Okay? That's what Mr. Burgers would tell us. This is called, for a liquid crystal, we call it anchoring, right? A liquid crystal cell is rubbed to make the liquid crystal orient a specific way on the surface. So here I have essentially an anchoring condition on the boundary, and let's see what happens. So from the point of view of the Monte Carlo simulation, I just fix those spins and I don't let them change. Only the ones in the middle can change. And I quench the system below the phase transition temperature, and lo and behold, 1 topological defect. So the total topological charge is constrained by the nature of the boundary. Okay. Now I did the same thing with a total of 8 pi rotation around the whole box. Okay. I didn't make a movie, I just have the one thing there. And you can't tell which ones are positive and which are negative, but I think I marked them. So green, I'm sorry if there's anybody here who's red-green colorblind I should have used. Is there anybody here who's red-green colorblind? Oh, thank goodness. Screwed up. I just know green means go, red means stop. It seemed like nice 2 colors to use for +1 and -1. And so we have plus, minus, plus. Actually, there's a minus there. I think I forgot to circle. Plus, it was late last night. So let's see. 1, 2, 3, 4, 5, 6, 7. Wait, I can't. What am I counting? Let's count green. 1, 2, 3, 4, 5, 6, 7, 8, 9 green ones. No, how many?
There's another 9. It's just another one.
No,
There are 9.
There's one more red one I forgot to mark there.
There's another red one.
There's another green one?
Down.
Right.
No, right.
Cancel the right.
Right.
I'm confused. Right there. Okay.
It's a red one.
That's a red one, and that's a red one. I think I put in 8 pi rotation, so there should be 4 more green ones than red ones. Did I not get that? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. I'm confused. Maybe I only put in 4 pi rotation. Maybe there's only 2 extra. I'll look at the code. We'll see. Okay, next question. What if you have a free boundary, not a fixed boundary? Okay, if you have a free boundary or a fixed boundary. Again, we can go to metallurgy to understand. Everybody here had electrostatics at the undergraduate level. Do you remember the thing called an image interaction? Let's review. Here is a piece of metal conducting plane. Put a point charge near the plane and calculate its interaction. You know, what are the forces on it? What's the electrostatic potential? What's the electric field? What's the induced surface charge density? How do you solve that problem? You put an image charge of the opposite sign in a symmetric location on the other side of the plane. Okay? And that's imaginary. There is no charge there. Where is the charge actually distributed on the plane, right? But with this construction, you know by symmetry that the potential is uniform everywhere on that plane, and therefore from using that information you can calculate. If you can guess the answer, there's only one answer. There's a uniqueness theorem for solving the Laplace equation. So the same way you can use image interactions to solve problems involving defects and boundaries. So the first question is, if you have a free boundary and a defect near the free boundary, the construction is that there's an image of the opposite sign. The sum of those two things makes zero torque on the boundary, so the boundary is free, and then the defect is attracted to the free boundary and wants to annihilate there. Okay, I mentioned Romeo and Juliet before for positive and negative defect going together. I think in this case, if you think of a positive defect attracted to a free boundary, I think of the myth of, what was his name, Narcissus, who was attracted to himself in the mirror. So imagine, Narcissus sees the mirror and wants to run to the mirror and kiss the mirror and then annihilates on the mirror, right? So the defect is strongly attracted to the free surface and will annihilate there. If instead you have a boundary where you fixed, say, the spin to have a particular orientation and it can't move, the defect is repelled from the boundary. So you have these image interactions. So in that case, the image is the same sign and it's a repulsive interaction. So defects interact with each other and with boundaries. Okay. You can also have stress concentration at corners and cracks. If you want to tear something, if you have a little bit of a pre-crack and then you rip it, it's easier than starting with nothing. Like if you wanted to tear a telephone book, if someone took a saw and started, it's easier to tear it, right? Pre-crack. The same thing happens. And I'm going to show you. This simulation was done a long, long time ago by a high school student working for me, but I'll tell you about it. So this is the simulation of the XY model. It's not Monte Carlo. It's another type of simulation I'll tell you about later. But the idea is that you can't see them, but there are spins on the top half that are all rotating clockwise, and spins on the bottom half that are all going counterclockwise. This side is free, and this is a crack, which means the XY interaction is severed across the two sides of this line. And what's happening is as the system is being twisted, the two sides twisting in opposite directions, it creates a stress concentration at the tip, and vortices are spewing off the tip that is an exact analog of having dislocations popping off the tip of a crack in a ductile material when you shear it. So there's all kinds of wonderful analogies between metallurgy and so dislocations in crystals, especially screw dislocations, and defects. So I think I'll just tell you, well, maybe this is a good place to stop. Let me think what else I was going to show you. I think maybe I'll stop there. We have a few minutes for questions, and you guys must be tired because it's right after lunch, and I'm supposed to finish by 3:30, right? So I have 5 minutes approximately for questions, and then a little stretch time.
How do defects influence the shape of a drop, if you were to think about
A drop of liquid crystal or a drop of a vesicle? For a drop of liquid crystal, that's a really deep and interesting question. There's a thing called a tactoid. It looks a little bit like a lemon. So a droplet of liquid crystal that has a pneumatic director, say parallel to the long axis of the lemon, has a defect on both sides. Ivan, is that a bujum on both ends? And the bujums repel from each other and they pull the drop into a lemon shape. For the vesicle, that I'm going to be telling you about. So for instance, in the vesicle, in one of our later discussions, so in the vesicle, if you have a phase transition from a smectic A-like untilted membrane to a tilted one, it's like an XY model on a fluid vesicle, and the defects can certainly influence the shape.
Are there any tricks for getting over the artifact introduced by this energy barrier?
Sure, but then it's not necessarily the XY model. It might
Okay.
be an altered model. It might be a continuum version of the XY model. You can use finite element instead of discrete simulation.
Are there similar automator type modules we can use?
I don't know. Does anybody else know cellular automata type models? And what if you wanted to replace the value of the spin at each site with the sum of its neighbors? The problem is everything's between 0 and 2 pi, modulo 2 pi, so getting an average is not always easy.
So I think I missed what causes some defects to be returned by free boundaries and others to be attracted by free boundaries.
Okay, all defects are attracted to free boundaries because they can annihilate there.
Okay.
And so then you can get rid of a defect from the system and lower the energy of the system,
Regardless of their charges?
regardless of their charges. All defects are attracted to the free boundary. The issue is that the image charge, if you want to use the image charge construction, is the opposite charge. So if a positive defect is near a wall, it imagines that it sees a negative defect at a symmetric location and wants to annihilate there. Okay, but if you have a fixed boundary, the image is of the same sign and it's a repulsive interaction. So the defect wants to run away from the boundary. Yes.
Do we have a similar sort of barrier or that energy bound barrier thing that you had between defects that you needed?
Like if they want to pair annihilate?
Yeah.
Yes.
The boundary, I mean. So we've got,
yes.
Yeah.
So if they're far enough from the boundary that the attractive force is too small to overcome the barrier, they won't go out.
Okay.
And actually, I was really frustrated by that yesterday. I was running all kinds of simulations to try to see the defects exiting at the free surface, and at the temperatures I was running, the defects weren't mobile enough to escape. That happens in crystals too. If the crystal is particularly cold, the defects have very low mobility and they won't exit from the free surface even if they're nearby. Of course, in real crystals, dislocations can also entangle. There's no entanglement in 2 dimensions, right? There's no way to tie a knot with point defects. But they can also, did you see they form those structures? Like, you could imagine that they might want to pair annihilate, but the Pyros Barrier stops them from annihilating. I ran a simulation on an amorphous, let's see if I can find it. On an amorphous mesh instead of, let's see, I need the ICAM. Here we go. I don't see it. It's probably here somewhere. This is the random mesh. So instead of using a square lattice, we just have a random mesh that was constructed through some stochastic process, and it can still trap defects. The difference is that in this system, the Pyros barrier is spatially non-uniform. Even the core energy of the defects is non-uniform, but it produces a very similar result. What's interesting about that is that we can put that random mesh onto a sphere. And so next time I will talk to you about XY models on spheres and donuts and all those things. And I think we better stop. Thank you.